In this video, we'll see the basic concepts of conservations of angular momentum and then how we could solve that. The problem is stated with a pendulum consists of two 3.2 kg concentrated masses positioned as shown on the light but rigid bar. Then the pendulum is swinging through the vertical position with a clockwise angular velocity of 6 rad per second when a 50-gram blade travels with a velocity 300 meters per second in the direction shown. Strike the lower masses and then become embedded in it. Calculate the angular velocity omega prime which the pendulum has immediately after impact, and then find the maximum angular deflection theta of the pendulum. So this is the question. And then even if you look over the animation, once the pendulum reached over this position, it strikes with the blade and then it will embedded with the blade and then reverse its direction. And then the main concept is that during the impact, angular momentum is conserved because there is no any external system. So the bullet and then the pendulums are just considered in one system. So we can use the conservations of angular momentum for solving the angular speed after impact. And we know that the system will rest when the maximum angle happens. That means when it finishes its kinetic energy, and then it will stop at that position. So we can use the conservations of energy. That means after impact there will be a conservations of energy. So let's just see how we can solve it. Now if we start from the given part, the mass of bullet is given as 50 gram, which means 0.05 kilogram, and then the velocity is given at 300 meter per second. And then we know that the system is swung with the angular velocity of omega here. So just let's evaluate V1 and V2. We know that since it is rotating in the clockwise direction, at the moment of impact, let's say this is particle 1 and then this is particle 2. So particle 1 will have a velocity in this direction. So V1 is equals to R1 times omega. V means just the distance from the center to this. It is given as 200 millimeter. It is 0.2 meter. So it will be just 0.2 times omega is 6. So it will be 1.2 meter per second. And the same thing for the velocity of particle 2. So V2 is equals to R2 times omega, and then it will be 0.4 is given here. So 0.4 times 6, it will be 2.4 meter per second. And then M1 is equals to M2 is given as 3.2 kg. Now the required parameters are just to evaluate omega prime and then the maximum angle theta. So let's just apply the conservations of angular momentum, because during the impact the angular momentum is conserved, no external force or moment is applied over the system. So since there is no any external thing, the moment will be conserved during the impact. So if angular momentum conserved, we know that h01 is equals to h02, which means before impact and then after impact the angular momentum will be the same. Now to find out this part, this is V1, we know that, and the perpendicular distance is, let's say that is R1, and then in this case it is 0.2 meter. And then for particle 2 we have V2 at a distance of R2, which is 0.4. And then for the blade part, we know that it is given us at an angle of 20 degrees. So we'll have two components. One component is in the X direction, and then one component is in the Y direction. So this one will be velocity of bullet in the X direction, and then this one will be velocity of bullet in the Y direction. But the velocity of bullet in the Y direction might not have any moment effect on the system, so it might not have any arm length. That means the arm length related to this one is 0, but instead of that the velocity in the X components will have the radius, or will have a perpendicular distance R2, which is 0.4. so this will have an impact over the system, so we don't need to use this part. So velocity of bullet in the direction will be VB, that means 300 times cos 20 degree. And then if you make that, you'll get 282 meter per second. Now let's evaluate the angular momentum before impact. That means h01. So which is equals to, now for the particle 1, since the counterclockwise is positive, so the particle 1 will have the effects in the clockwise direction, so it will be negative, but the bullet will have a clockwise effect, so the bullet part will have the positive, and then particle 1 and particle 2 will be in the clockwise direction, so they will have a negative sign. So which is equals to negative R1 M1 V1 minus R2 M2 V2, and then plus R2 times mass of bullet times velocity of bullet in the x direction. We know every parameters with numbers, so if you substitute all those numbers, finally we'll get h01 is equals to 1.7982. So this is just the angular momentum at O just before impact. Now let's just evaluate the values after impact. So just after impact, we'll have h02. So h02 is equals to, assume the counterclockwise is positive at the previous one. So in this case, assume the system will swing in the counterclockwise direction and with the angular velocity of omega prime. So if this is the case, since the systems are embedded together and then swung about the point O over here, so the final angular momentum for the system will be evaluated in this way. That means h02 is equals to, for the particle 1, R1 M1 and then V1 prime, plus for particle 2 and particle of the bullet, they are embedded together and then they have the radius of the arm. That means R2 times mass, in this case is mass 2 plus mass of bullet times their velocity is V2 prime. So this will be the final angular momentum, but we know that in this case V1 prime and V2 primes are the same as the previous one. That means they will be R1 times M1. So V1 will be just R1 times the new angular speed. That means it will be omega prime. So plus R2 in bracket M2 plus MB times V2, in this case is R2 times omega prime, because the velocity will be changed after the impact, but the angular velocity will be constant for all particles since they are embedded together and then rotate with the same angular speed. So this will be h02. So if we substitute just the numerical value, finally we'll get h02 is equals to 0.648 times omega prime, because the other parameters are known but omega prime is unknown. But we know that from the conservations of angular momentum, h01 is equals to h02. This implies that 1.7982 is equals to 0.648 omega prime. So the only unknown parameter is omega prime, so divided this with 6.648, divided this with 0.648, and then finally omega prime can be is equals to 2.775 rad per second. This is the new omega. That means the system is rotating with the angular speed of 2.775 after the impact. Now just after impact, the energy is conserved. So if the energy is conserved, now let's just evaluate the maximum angle theta. So the maximum angle theta will happen when the system becomes at stationary. That means when its speed reduces into 0. So let's just use the initial and the final conditions of the system. Assume the initial condition is when the particle starts just after the impact, and then the final position is when just the system becomes at rest, that means at this position. So, and then let's take our reference as a horizontal line here. So now this is the initial condition, and then this one will be just the final position. Now this is just the angle theta, that means the maximum angle theta when the system becomes at rest. We know that this is R1 and then this is R2. So with refers to this, we are referring from this position. Let's take out the initial and the final energy on the system. So we know that kinetic energy at the initial plus potential energy at the initial with respect to the gravity plus the work done from the initial point up to the final point will be equals to kinetic energy final plus potential energy final. Since there is no any external forces, so there might not be any work done, so it will be 0, and then the system will be at rest, that means the final kinetic energy will be also 0. So finally we'll have kinetic energy, that means initial kinetic energy plus initial potential energy due to gravity is equals to potential energy of final due to the gravity. So this will be our new equation just to govern the positions of the particle just before it comes to rest or at theta maximum value. Now Ti, or kinetic energy, initial kinetic energy, is equals to half m1 v1 prime squared plus half m2 plus mass of bullet times v2 prime squared. Now let's insert the numerical values. So finally we'll get kinetic energy at the initial condition is equals to half m1 is 3.2 times v1 prime is, so r1 times omega prime the whole squared plus half of m1 plus m2 is 3.25 times v2 prime will be just r2 times omega prime the whole square. So we know r1, we know omega prime, so if you substitute all these numbers, for finally you will get the initial kinetic energy, which is equals to 2.495 joule. So this is the initial kinetic energy. Now for the potential energy, that means related to the gravity, if we just look the system, so particle 1 is beyond our reference, so it will have a positive impact on the system, and then for the particle 2 it is just below our reference, so it will be negative. That means potential energy due to gravity at the initial condition will be equals to m1 g1 times h1. h1 in this case is r1, so minus for the second case m2 plus mass of bullet times gravity times r2. So we know all the values, so if you substitute that, finally you will get the value of negative 6.4746 joule. So this is just VGI. Now for the final condition, let's just assume this is our final condition, as we know that when the particle is over the maximum part, it will have on this position, and then their elevation can be just from this point to this one for element 1, and then from this to this for the particle 2 and the bullet part. So if you just take this one as just h1, let's say this is h1, and then this height is just, let's say this is h2. Here this length is r1 and then this is r2. So we know that h1 is equals to, if this is theta, this one will be also theta, so h1 will be equals to r1 cos theta, and the same thing h2 will be equals to r2 times cos theta, so r2 times cos theta. Thus h values will be used for the final gravity energy. So final gravitational energy is equals to m1 g times h1, and then minus m2 plus mb times gravity times h2, because we are assuming that particle 1 is beyond our reference and then particle 2 and the bullet is below the reference plane, so that is why this is negative as we discussed previously. Just substitute the numerical value, then finally we'll get VGF is equals to 3.2 times 9.81 times H1, in this case is R1 cos theta, minus 3.25 times 9.81 times, now H2 is R2 cos theta. So this implies that finally VGF is equals to, the only unknown parameter is cos theta, so the other parameters are numbers, so finally it will give us negative 6.4746 times cos theta. So this is just the final gravitational energy. Now by using the previous derived equation from the conservations of energy, we can substitute all parameters, then we can get the unknown parameters. That means Ti plus Vgi is equals to Vgf. So let's substitute all the values. We know that Ti is given here, and then Vgi is just evaluated here, and then Vgf is evaluated here. So substitute all these values, then we'll get 2.495 minus 6.4746 is equals to minus 6.4746 times cos theta. So the only unknown parameter is here cos theta. So if you rearrange that, so we'll get cos theta is equals to negative 3.9796 divided with negative 6.4746, and then finally it will be 0.6146. So theta is equals to cos inverse of this number, that means for 0.6146. So cos inverse of this finally will be 52.08 degree. So this is our final answer for the maximum angle when the system becomes at rest. And then previously we have calculated omega prime, so omega prime will be also our answer. So this is it.